All right, let's get started. Today, we're putting on our architect hats to conduct a technical design review of a mission-critical component, a distributed messaging queue. This is the kind of system that serves as the backbone for high-throughput, low-latency enterprise environments. So let's really dig into the design. So let's just level set on the basics. A messaging queue is fundamentally a buffer. It's an intermediate component that sits between producers who are sending messages and consumers who retrieve and process them at their own pace. The key concept here is decoupling. It allows the producer to fire and forget while the consumer can process that data whenever it has the capacity. It's an absolutely foundational pattern.
Now, before we even look at the architecture, any system like this has to be vetted against some core non-functional requirements. First, durability. We can't lose a single message, period. Second, scalability. It has to handle massive load spikes but also shrink resources when things are quiet. Third, availability. The system must stay operational even if some of its components fail. And finally, performance. We are talking high throughput and super low latency. These are the absolute table stakes.
Okay, here's our agenda for the review. We'll start with the ordering conundrum, then jump into concurrency without locks. After that, we'll break down the architectural tiers, look at how metadata is managed at scale, cover replication and cluster management, and wrap up with the dimensions of scalability. Let's dive in.
So the first major design consideration is one of the most fundamental trade-offs in distributed systems, and that is message ordering. It's this constant battle between performance on one side and consistency on the other. And here's that conflict, laid out plain and simple. On one hand, you've got strict ordering, which preserves the exact FIFO, first in, first out sequence. But look at the cost. It requires online sorting and request serialization, which is a huge performance hit. On the other hand, you have best effort ordering. It just places messages in the queue as they arrive. The benefit? Way higher throughput and much lower latency. The trade-off is clear. You lose that strict ordering guarantee. For most high-throughput systems, this is the compromise you have to make.
All right, let's build on that. The next big challenge is managing massive concurrency from potentially thousands of producers and consumers hitting the system at the same time, all without the system grinding to a halt under lock intention.
So this brings us to the crucial question, right? How can we manage race conditions and prevent data corruption from all that simultaneous access, but do it without taking the massive performance penalty of traditional locking mechanisms?
And this is the proposed solution. It's a really brilliant lock-free design. Instead of dealing with complex, slow application-level locks, you just let the operating system's own buffers queue up the incoming requests. Then, you have a single application thread for producers and another one for consumers that just pulls from that queue and processes everything sequentially. The result? You completely avoid race conditions without a single lock. And that's how you unlock that insane throughput.
Okay, so with those core concurrency and performance trade-offs addressed, let's zoom out and examine the system's high-level architectural blueprint. It's a classic tiered design, which is exactly what we'd expect for a robust distributed system.
Let's trace the request flow here. It starts at the load balancers, which distribute the incoming client requests. From there, requests hit a stateless front-end service, which handles validation, authentication, and routing. That front-end needs to know where to send the message, so it queries a metadata service. And that service points it to the correct backend service, which is the core data layer where the queues and messages are actually stored. This separation of concerns is just critical for scalability.
Now, let's look closer at that front-end service. The fact that it's stateless is key for horizontal scaling. Its responsibilities are crucial for protecting the downstream systems. It handles the obvious stuff like request validation, but also authentication and authorization, with heavy caching to avoid hitting an auth service for every single request. And this is a big one, request deduplication, often using hash keys, which prevents all sorts of bugs from duplicate processing, a really busy, important layer.
The metadata service is basically the system's directory or its service discovery layer. It stores and manages all the queue metadata, things like its location, its configuration, its partition keys. It's the critical middleware that sits between the stateless front end and the stateful data layer. When a queue is created or deleted, this is the service that's responsible for updating those metadata stores and caches everywhere.
And finally, we get to the backend service. This is the real workhorse of the architecture. It's where the actual message queues are hosted. Its core responsibilities are data storage and, critically, data replication across different nodes to guarantee that durability requirement we talked about at the start. Okay, so that metadata service is obviously critical. But how does the metadata service itself scale as the system grows?
You can't just have one giant metadata database. That becomes a bottleneck and a single point of failure. You need strategies for growth.
The design here proposes two very different strategies based on scale. For smaller datasets, the approach is full replication. You just copy the entire metadata set onto each and every metadata server. It's simple, and any server can handle any request. But for large-scale deployments, that's just not feasible. So you move to sharding. You partition, or shard, the metadata across different hosts, and the front end uses a mapping table to figure out which shard has the data it needs.
We've mentioned replication a few times now, but let's scrutinize exactly how the system manages data copies and cluster health. This is all about ensuring that durability and availability when things inevitably go wrong.
So the design uses two distinct types of cluster managers, which is a pretty interesting separation of concerns. You have an internal cluster manager that operates within a single cluster. It's responsible for the low-level tasks, knowing about every node, listening to heartbeats, managing host failures. Then you have an external cluster manager that operates at a higher level across different clusters. It doesn't care about individual hosts, it just monitors the health of each cluster as a whole and manages things like cross-cluster load balance.
For the actual data replication, the design employs a very standard and robust pattern, the primary-secondary model. For any given queue, one node is designated as the primary. It's the leader, and it's fully responsible for receiving all requests and then coordinating data replication out to the other nodes, which we call the secondaries.
So the crucial point here is that the primary host acts as the single source of truth for its queue's state. It receives all incoming requests for that queue. It manages the replication of messages to all of its secondary hosts, and, just as importantly, it's also responsible for deleting the message and all its replicas after it has been successfully processed.
Okay, finally, let's review how this architecture is designed to scale horizontally. And this is key. It scales along two completely different dimensions, handling an increase in messages and handling an increase in the number of queues.
The first dimension is message volume. The system has a built-in auto-scaling mechanism. When a specific queue's message volume hits an 80% capacity threshold, that triggers an automatic expansion of resources just for that queue. And of course, it can shrink those resources when the load goes down.
But what if the number of queues increases dramatically? That's the second dimension. To handle more queues while ensuring performance isolation between them, the system simply scales by commissioning entirely new servers. You're just scaling out the whole cluster.
So, to summarize, this design is built on several really powerful patterns. We've got that lock-free concurrency using OS buffers for high throughput. We have a stateless front end with aggressive caching and deduplication to reduce upstream load. It's a classic tiered architecture for great separation of concerns, and it has this dual-mode scalability, with different strategies for message volume versus queue count. A very solid foundation.
This architecture looks solid for handling data and metadata within a region, but it leaves us with one final massive question. What happens when this system has to become globally distributed? What new challenges emerge around cross-cluster networking and latency? Because at that point, your main bottleneck isn't the servers anymore. It's the speed of light itself. And that is a much harder problem to solve.